Let's get started. All right. First thing, you guys all should have got an email about the alternate exam time. Yes, I saw a bunch of you already responded. So if you didn't get that email, please check your schedule for Monday, October 11th from 7:15 to 8:45 p.m. And if you have a conflict, and only if you have a conflict, here on our course Canvas page, if you go to the midterm, they're just week modules. So the week that it would fall on, request for an alternate exam time. Click on that button, tell me why you need to move your time, and I've got an alternate exam time set on there from 3:30 to 5.
Wait, the alternate exam time is
3:30 to 5 for the alternate exam time. Yeah. And if that doesn't work for people, I'll move it to 7 a.m. Right? So that's how I make sure to know it works. Okay. So McBurney students, we got time and a half. You also should have received an email. Heard back from a couple of you too. So again, if the time that I have for that exam doesn't work, please contact me. All right. Moving on. Chapter 3, Newton's second law, F equals ma. The only equation we really need to talk about today. So, where I started last lecture, I tried to provide a little bit of insight as to what we were doing in Chapter 2. Chapter 2, we were just chasing particles' locations around in xy, in nt, in polar coordinates, if they were attached to a string, if they were connected geometrically. It was all so that we could write this acceleration down. So now we have that tool to be able to use. Let's go ahead and put it to use. So when we're doing these sum of forces problems, it's going to look a lot and feel a lot like what you did in statics. You're going to have something with forces acting on it. But now instead of it being in static equilibrium, so the force is equilibrating to zero, hey, there's going to be some acceleration we have to deal with. So that's going to cause these particles to accelerate. We have to track that now. Or vice versa, we can look at it like, hey, we know this thing's accelerating. Hey, what kind of forces are acting on it? We'll just run this equation backwards, right? So today we'll look at it in a Cartesian system, x, y. Next time we get together, we'll start looking at it in polar and nt coordinates for curvilinear motion. So we'll ease you into this a little bit. So I got a goofy little example. This is my spaceship. It's got wheels. All right, so I got my spaceship here. And it's got an ion thruster. So at the back of this, it shoots some little ions, some little particle dust. And the force acting on it, this thrust, from releasing these particles, .1 newtons. You think, what's 0.1 newtons? 1 newton, about the weight of an apple. 0.1 newtons, about the weight of 2 nickels. So this spacecraft, here in outer space, floating around, far away from Earth's gravity or the sun, just in deep space, it's being thrusted by the weight of 2 nickels. So you can think of someone like sitting behind it and just like blowing on it. But in space, there's no drag acting on this because we're in a vacuum, right? So there's nothing working against us in this direction. So if you think about this from your statics class, we've got no weight going down because this thing's in space. There's no gravity. So my FBD is pretty simple. If we were on Earth, we'd have a force of drag. In space, that's nothing. So when we look to do our equations here, maybe I have a coordinate system, x and y. So I'm going to do sum of forces in the x direction. Sum of forces x, positive to the right, I have my thrust, 0.1 newtons. This is equal to, I like to draw it on my picture too. My picture is equal to a free body diagram, and now kinetic diagram. We just call this KD. So kinetic diagram. For this part of class, kinetic diagrams aren't super exciting yet because we're modeling everything as a particle. So we just draw a dot. That's how we're modeling this. If we think from our free body diagram side, yeah, we're still modeling this thing as a dot. But I had this awesome drawing of a spaceship, so I was going to use it. Right? But all of our forces are actually just acting through this point, or our concurrent force system, if we want to get fancy. Everything's operating through this point. So for our point, the center of gravity, this is the part we're tracking. So if I'm looking at an XY system, kind of the first thing we do with these problems is say, what coordinates am I going to use? Today we've only learned XY, so we're going to stick with that. My kinetic diagram side, m times acceleration in the x direction, m times acceleration in the y direction. This drawing and this drawing make our sum of forces equations. So sum of forces in the x, all I had was my thrust. Jump over my kinetic diagram. What do I have in the x? M times ax. The y direction, positive going up. For my free body diagram, I got nothing. I'm in deep space here. For the y direction, MAY. AY is 0. I got no acceleration. Our spaceship weighs 1,000 or has a mass of 1,000 kilograms now. So if we do this, we can get an acceleration. AX. 0.1 divided by 1,000, so that's 0.0001. And it's acceleration, so it's meters per second squared. So this tiny little force blowing on the backside of our aircraft or our spacecraft is creating a tiny, tiny, tiny little acceleration. So NASA's using these ion thrusters. They're not using them to blast off of Earth because they produce tiny little forces. But they're using them in deep space where they're going to produce a tiny little force where there's nothing slowing us down. And they're going to be able to have them going for years. You know, it's like, hey, I want to send this thing, I don't know, super far away. So then they turn on this little ion thruster and let's let it go to town for a year. So what does that look like? Let's say this thing is firing for 10,000 hours. 1 hour is 3,600 seconds. So I got 3.6 times 10 to the 7th seconds. I'm going to fire this thruster for 10,000 hours, about a year. My V final, with a constant acceleration, is my initial velocity plus my acceleration times time. Maybe I got this thing parked in space and it's not going anywhere for now. So it's 0. After a few seconds, it's not going very fast. But after 10,000 hours, this thing is going 3.6 kilometers per second, or 8,053 miles per hour for those of us who prefer car readouts. So, hey, tiny little force, nothing slowing us down. We can get going pretty darn fast in outer space. So, kind of a neat little example, silly, but it helps to show the point. How are we going to solve these problems? We're going to draw free body diagrams, just like we did in statics. All the external forces we know. Weights, cable tensions, we'll talk friction, we'll talk springs today, external forces. What's it equal to? Kinetic diagram. Mass times acceleration in the coordinate system we've chosen. Next step, all we're going to do is write equations. Sum of forces x, sum of forces y, If we had a z direction, we could do that as well. Set of equations, set of unknowns, solve it. Easy. The difficulty might be, what if you have more unknowns than equations? We got to bring in some more info. And that's what we did a little bit of last time we got together. Maybe you have a geometry that links these things together. You pull one rope, the other side goes. You sit on one side of the teeter-totter, the other side comes up. If we have more geometric information where we can maybe link some accelerations, we can solve some more stuff. So that's what we do. All right. So for this crate, modeled as a particle, think about how you would do this. Say, hey, all the forces are acting through our center of gravity. That's our concurrent force system. And we want to write all the external forces on this. So now our crate is here on Earth again. So just like you would do in statics, we've got mg going down. We've made a cut through the rope twice. So we've got 2p going up, or T if you like cable tension a little better. Well, in statics, life was good. You said, hey, P is this equal to mg over 2. Done, you're out of there. Right? Here, not so lucky. FBD side is equal to our kinetic diagram. So I got mass times acceleration in the x, mass times acceleration in the y. X direction, nothing. In our free body diagram side is equal to max. My eyeball just told me that that was 0. I could have written out the equation. Maybe I should have even done that on day 1, but playing this fast and loose here. So let's write out our other equation. Sum of forces y, positive going up. I've got 2 times our cable tension P minus mg. That's equal to our kinetic diagram side, may. All right. So what's going on with this pulley? Take a look at the external forces. I've got 2p going up, mg going down. If 2p is greater than mg, this side is positive. Right? If 2p is bigger than this, we're heading up. We're accelerating up. If we've got 2p is less than mg, so this side will be negative. What did I just, okay. Do no one even said anything? Okay, I drew a less than sign. So if we got 2p less than mg, this side's going to be negative. So this thing is accelerating down. And I'm going to write the word excel, just so that we know, like, hey, if 2p was equal to mg, static equilibrium. So if it was initially going at some velocity, whether that was up or down, we would be maintaining that exact same velocity. We wouldn't be slowing down or speeding up. Or we could just be sitting there still if it had 0 initial velocity. So this tells me that acceleration in the y is equal to 0. V doesn't necessarily have to be 0, right? If it had some initial velocity, it's not slowing down or speeding up. It's just not changing that velocity. I don't know, is there any other cases? I guess the last case could be P is equal to 0. I came through and I cut the cables. Now this thing's just free falling. So if P was equal to 0, this would give me mg is equal to m ay. Ay is equal to g. Our acceleration is just what gravity is doing. And I lost the minus sign here, so. Free fall. Pew! Nothing's slowing us down. We're just going and accelerating as fast as gravity will allow. All right. These are pretty easy. If you can simply draw the box and put some forces on it and write your sum of forces equations, life is good. But we got to make it a little harder than that. So we'll look at today forces due to springs. We'll look at forces due to friction. Let's try to complicate things a little bit. All right, so friction. In statics, you probably had static friction force using Coulomb here. Our static friction coefficient, mu static. Your static friction force I'm going to call that max. So our maximum friction force that we could have before this thing would start sliding would be mu static times the normal force. So the normal force, I've got maybe a block on a surface here. mg is coming down. And my normal force is equal to mg. How hard can I push on this thing before it starts sliding? That's what we're trying to figure out. So we'll do some problems like this, so I won't finish this one completely. But you can have a condition for no slip. So here, our friction force is less than mu static times n, so no slip. Less than or equal to mu static times n. I got my fancy notebook. If I set it on this table, right now I've got weight coming down, got a normal force coming up, but nothing trying to make this thing slide, right? So its maximum frictional force that it can have, this table's got some frictional coefficient, 0.2, 0.25 actually. It's got a normal force right now, mg working down, so I know it can handle a frictional force of 0.25 times its normal force. But right now, there's no need. There's nothing pushing this thing. But if we started lifting this thing, right? Okay. Now my weight vector is like tipping, and part of that weight vector is pushing us along the direction we want to go, right? So it's got a normal and a tangential component. So the higher and higher and higher it gets, more and more of this weight vector is pushing us along this surface to the point where we get to impending slip. So when you get to impending slip on this table, here's my table. We've got mg going down, normal force, and I've got this static friction trying to hold back force of friction. And at impending slip, we've got our frictional force is equal to mu static times n. So at the moment it wants to begin to slip, we've hit our max. If I went any higher, like, it's going to want to go, it's going to want to go. This is a sticky table. Oh, crap. Okay, so once it starts sliding, though, that's no longer our frictional force. So the assumption we make with Coulomb friction is that your static friction coefficient, mu static, is always greater than your kinetic friction coefficient. Probably greater than or equal to. So you need some force in order to get this thing to break away. But then once it's sliding, it's actually going to have less frictional force once you've begun sliding. This is kind of the idea behind anti-lock brakes in your car, right? So you're driving on the ice, you slam the brakes, your wheels start skidding. So they've gone from a static case to a dynamic case with kinetic friction. And as these wheels are slipping, that force slowing you down is less because the kinetic friction coefficient is less than the static friction coefficient. So your car is just sliding along. So what does your car do? It's like, I don't like that. It releases your brakes until it feels the wheel regain traction. So kind of on, off, on, off, on, off with your brakes to force you to use the static friction coefficient as opposed to the kinetic friction coefficient, because you're getting better stopping power. Even though you're letting go, you're getting better stopping power if you're in that static condition as opposed to a dynamic friction coefficient. So why we need anti-lock brakes? When you feel that funny pedal kicking back in the winter, that's what's happening. So here's friction. One interesting thing with friction, or the hard part, I guess, about friction, is that our frictional force is going to oppose motion. So here, I got a table, I got my book. When I lifted the table up in the air, my book wants to slide down, so my friction force slides up. Here on the screen, we've got kind of another mess. We've got a two-body system. So what does friction look like in this system? Just going to separate them and make them big so we can see. All right. Maybe just some practice. Draw all the forces acting on this thing for our free body diagram. We're going to have all the forces acting through just the centers of mass. So we've got the mass of A times gravity. Here we've got the mass of B times gravity. We've got a normal force pushing up, NB. And we've got a force between these two. The normal force between A and B. Okay. I've taken the system apart. So in my brain, when I put this thing back together as one system, this internal force better cancel. So while it's pushing up on A, it's pushing down on B. So when I take this and I click it back together, plus and a minus, poof, they disappear. Right? So for this problem, we've got that there's some velocity of A relative to B. Okay. This kind of brings us back to last time we got together. So let's say that the velocity of A is 3 meters per second. The velocity of B is 1 meter per second. These are both to the right. So our relative motion equation, the velocity of A is equal to the velocity of B plus the velocity of A relative to B. So I said I had 3, I have 1. This guy has to equal 2. So the velocity of A relative to B is equal to 2 meters per second. How do we interpret that with our brains? We say, hey, A relative to B. I take B, I don't let it move. I look at A, what's A doing? It's moving 2 meters per second. If I rearrange this and did this the other way, and I wanted the velocity of B relative to A, I would hold A still, and I'd look at B. And it would look as if B was going in the other direction. So it's just the opposite, so just minus 2 meters per second. So we don't really need that one. It's just for fun. But when I want to think about these friction arrows, what's happening here? I need to figure out the relative velocity. So if B is standing still, and A appears to be moving 2 meters per second. It's moving this way. All right, now that I know the relative velocity, I can say, hey, the friction opposes that relative motion. I could look at my equation for V of B as the, with respect to A, pin this one still, say B is moving this way, so friction has to oppose. Or I could think of it, I only need to figure out one direction. It's an internal force, so that when I put these two things together, they better cancel. That's the way my brain works. Try to figure out how that friction is acting on one of the bodies, and then equal and opposite on the other body. So for this system, look what we got. We got two bodies. So you're going to have two FBDs, 1 and 2. You're going to have 4 sum of forces equations. You're going to have 2 x's and 2 y's to figure everything you need to know. And then when you think, well, what do I know that's common between them? The normal force is common between them. Forces of friction are common between them. And you can go about solving these problems. So you might need to know something. Another way we can look at this and kind of make sense of what's happening is that, hey, if A is sliding on the top of B and B is standing still, that friction that A is putting off on B is causing B to also move in that direction, that same direction, which is what a friction force is doing. Just go in there. And in this case, it happens to be a little bit slower. I didn't draw any other external forces, so we don't know if there's somebody pushed this or whatever happened to it, but we have ended up at this state, and now we can try to figure out how things are moving. All right, springs. You guys do springs and statics, right? Yeah? Okay. Spring force, F sub s, is equal to my spring constant times the displacement. Sometimes we get a little fancier. We say I have some spring constant times L final minus L initial. Hey, that's just displacement. The one thing we do have for this, the way I've drawn this and the way I've written it, is that this is a constant times a displacement. This is a linear spring. So linear spring from a linear system. So linear means line. Nothing fancy. So I have some force. I've got some displacement. Maybe it's x. Maybe it's delta. Maybe it's L final. Just changing the length of the spring, right? And if this is linear, my slope here is k. If I move this thing 1 foot, I get a spring force of 10 pounds. If I move it 2 feet, man, I better get 20 pounds. Linear spring increases linearly. You might have a fancy spring. Your spring might be linear to a certain extent, and then you overstretched it, and then it dies. Right? So maybe it kind of tapers off here. Maybe you've got a spring that is nonlinear, and its stiffness changes as a function of x squared. I don't know. You guys are engineers. You develop fancy springs. Typically, when you see a normal house spring and coils, as we pull on them, they behave linearly. If we've got a beam, and someone pushes on it, it bends. Maybe that acts like a spring. Behaves linearly. Until we start yielding things. You'll learn all about that in mechanics of materials. All right, so springs sounds like you guys are already experts. No need to reteach that. Last point, before we just get into it. Newton's second law in inertial reference frames. When we're doing these sum of forces equations, we have to have our initial coordinate system that we're looking at be inertial or non-accelerating. So generically we say, hey, it's on Earth. Earth is doing some funny stuff. It's spinning here, it's spinning around the sun, it's spinning in space. Like, you can make the case for the fact that that is not inertial, right? You just learned all about polar coordinates and accelerations. Hey, I'm sitting on Earth. This is my reference frame. We're going to assume that Earth is inertial. But maybe an example that isn't. Maybe I'm on an elevator. So here's my elevator. Here I am. I'm trying to weigh myself on an elevator. I'm actually standing on that elevator, but I've just separated us so I can draw on our forces. Big X, big Y, that's my inertial reference frame. Little x, little y has been attached to the elevator. It moves with the elevator. So, free body diagram time. My weight is mg. Between me and the scale is some normal force. That's all the scale knows, right? It doesn't know my mass times gravity. It just knows whatever's happening between it and my feet. So sum of forces in the big Y, positive heading up. mg going down. Acting on me. I'm looking at me. N going up is equal to mass times my acceleration in the y direction. Let's look at the normal force. So I rearrange some things. My normal force, kick this to the other side, is equal to mass times AY plus G. When you get in an elevator, all the elevators I've gotten in have been stationary when I got in them. But then they begin to move up or down, right? So if it goes from 0 to some speed, it has to accelerate. If this elevator is going up, G, that's us on Earth. We're going to assume that's constant. So normally, standing on Earth without Earth accelerating, or without my body accelerating, my normal force, mg, that's the weight that the scale would show. But if I've got us going up here, my AY is increasing. We've gone from 0, we're starting to accelerate up. I'm going to look pretty heavy, because this n is going to be higher than mg, because this is going to be positive value when I go up. If I want to feel good about myself, had a big Thanksgiving dinner or something, and want to weigh in, I get on the elevator, and I start going down. And I weigh myself. Because now my AY is going to be negative. It's like I'm looking good. Okay, so my normal force, what the scale would read, would depend on how this elevator is traveling. If we looked in an inertial or our inertial reference frame, we just did. But if we looked at a reference frame attached to the elevator, sum of force is little y. I'd have minus mg plus n. Still the force is acting on me. It's equal to may. But if I was taking a coordinate system and pinning it to this elevator, that elevator's spot, maybe like the creepy mirror in the corner, reference to me, I'm never accelerating with respect to that point. So I'm always moving in line with that elevator. So my AY here would be 0. So my scale would always read mg, just as if I was standing still. So Can't do that. Long story, lock your coordinate system that you're measuring your sum of forces and writing your equations with respect to an inertial frame. So it can be traveling, but it can't be accelerating. So if my, we'll just leave it at that. Okay. Got a couple examples to crank through, but first, technique, how are we going to solve these guys? Step one. There's a lot of writing here, but there's not really that much to think about. Step one. I guess read the question. Step 1B is FBD and kinetic diagram and coordinate system. In order to draw your kinetic diagram, you need to pick a coordinate system that you're going to use. Today you got essentially one option, XY. Once we get into next week, we'll learn polar and we'll learn NT, so life gets a little more complicated. But read the questions, draw your forces, draw your kinetic diagram. This is your sketch of the problem. Try to think about what you're trying to get done. Step 2, sum of forces equations. This should fall out directly from your free body diagram and your kinetic diagram. Here, let's count our unknowns and equations for that matter. If you got enough equations and unknowns, 1 to 1, 2 to 2, solve it. But if you don't, you probably need some geometric constraint. You might get that from ropes. You might get that from a lever. You might get that from two bodies that are contacting one another, slipping relative to another. It's putting together your equations. So, step 4, solve. Step 5, I guess, would be sanity check. Try to figure out, hey, does this actually make sense? I got an acceleration that is in the wrong direction. I got a compressive force on a rope. That doesn't work that way. So think about what you got and solve it. It's not a very detailed roadmap, but I think it's intuitive. Okay, I've got a motor at M here. And it's pulling the rope attached at an acceleration of 6 meters per second. So if I grab some point on the rope, it is accelerating towards the motor at 6 meters per second squared. We want to determine the towing force acting on the crate, given that the kinetic friction between the 50 kilogram crate and the inclined plane is 0.3. So, neglect the mass of the pulleys and the rope and assume they're frictionless. Okay. So let's unpack that a little bit. We've got a kinetic friction coefficient of 0.3. I told you the static friction coefficient is always higher than the kinetic friction coefficient, but once we're sliding, we only care about the one. So in this case, we know that this thing is already accelerating at 6 meters per second squared. So we've broken this crate free, and we're only worried about its kinetic friction coefficient. We're trying to find the overall towing force pulling up on this crate. So if you took yourself back to statics and you think, well, what's pulling on this crate? Maybe we make like a free body diagram cut through that, and we see that we got like 3 rope tensions. So our towing force will be these 3 tensile forces in the rope. What else do we have to worry about? We've got 50 kilograms times gravity, some mass coming down. I've got a normal force, and I've got friction. It's sliding, the crate is sliding up the hill because the ropes are getting shorter. So friction is opposing motion. Oh, that's our free body diagram. So we want to find the towing force, which I said was 3 times the rope tension. So my free body diagram. I'm just writing big T. You could write 3 little t if that suits you a little better. mg going down. Normal force perpendicular to our plane. Force of friction. So I'm a little loose with this in that it's a concurrent force system. So really all these forces should be acting on that center. I'd like to draw friction at the bottom. That's going to matter where we draw these forces once we start dealing with rigid bodies, because a friction force at the bottom could cause this thing to rotate if it wasn't going through its center. So for now, this is just me being a little loose with things. Kinetic diagram. So my step 1 was write our kinetic diagram and our free body diagram and choose a coordinate system. In this case, I could certainly pick an x and a y. And this system would be convenient to write mg. But then I'd have to rotate all these other forces. And I want to figure out what's happening in this inclined direction. So here, I am going to rotate my coordinate system. max, may. This way, when I start writing my equations, I really only need to worry about breaking this mg up into its 2 components, as opposed to breaking up friction, normal, and tension. All right, let's do our sum of forces. So we got sum of forces x, sum of forces y. All right, in the x direction, I've got t. I've got minus my friction force. And I've got some component of this mg. I got theta is equal to 30. So that's this angle here. That's minus mg, the sine leg of 30, or theta. This is equal to my kinetic diagram side. Mass times acceleration in the x direction. The y direction, what's happening along the plane, perpendicular to the plane. No t, no f, but I've got an n going up. And I got the cosine leg of mg going down. And that's going to be equal to mass times ay. One nice thing about rotating my coordinate system is I know right away something about my acceleration in the y direction. This crate is sliding along that plane. So as we're sliding along this plane, it's not moving up or down relative to that plane. So it's not accelerating up or accelerating down relative to that plane. It's just getting pulled along there. So if it's never changing its position, it's got no velocity. Its velocity is 0 and its acceleration are 0. So this ay is 0. If I left it in a traditional xy system, I would have had to break up that acceleration in the plane into its x and its y components, which would have been another pain in the butt. So from this, I get my normal force, mg cos theta. I need my normal force. That's my force of friction. So we know that our force of friction is mu k times n. So the force of friction, mu k times mg cos theta. We could take that and plug it in. Pretty close to solving this one now. Looking at our equations, thinking about what we do and what we don't know. We've already taken care of the y equation, so kind of jumped the gun on that one. But the x equation, we're trying to find our towing force. That's our question mark. Our frictional force, nailed it. We used y to solve for that. mg sine theta, we got an angle theta. We know we got a 50 kilogram crate, and we got gravity. Mass, again, times acceleration in the x. How is the acceleration in that plane? Well, we've got to relate that to the rope. So we know the rope is being eaten up. L double dot, the change in my rope length is equal to 6 meters per second squared. So I want to relate AX to that change in rope length. All right. We do that with a rope equation, just like we did last time. Kind of like we did last time, actually. So, let me pull up the picture again real quick. All right. I want to write my rope equation. I want to reference things from a fixed datum. That's kind of how we've done things for the rope equation. The point on this pulley is fixed because this rope is constant. Right? And then my datum that I'm going to pull to is that I'm going to pull to the center of this pulley because its location relative to that crate is also fixed. That's constant. And then therefore this little piece isn't changing length either, right? You're always going to have those two pieces of the rope. So this is like my SC. So if we looked at the length of this rope, I'd have 3 of these SCs, or XC, however you want to think of it. I've got some constant piece here that I'm going to sweep under the rug, but then I've got 1 piece of rope, 2 pieces of rope, 3 pieces of rope. I know how much that rope is accelerating. So if I took the derivatives now, I'd get L dot is equal to 3 velocity of the crate. L double dot is equal to 3 times the acceleration of the crate. And this happens to be, well, maybe I'll leave that for a second. Acceleration of the crate. So my L double dot, it's getting shorter by 6 meters per second squared. So the rope is losing length. That's equal to 3 times AC. AC is equal to minus 2 meters per second squared. So the acceleration of my crate is going opposite the direction of my datum at 2 meters per second. So it's going like this way. 2 meters per second squared, sorry. So that would be like my AX. Is actually heading up the hill. Oh, I'm out of time. Okay. But I've got it now. So if I jump back to my figure, my AX is equal to 2 meters per second. I plug that in. Everything else I know. So you can go ahead and plug them in yourselves, but you'll get a value of T, the towing force, 472.6 newtons. Pulling us up the hill. All right.
Where do we plug in -2 or +2?
Here we'd plug in +2 because it's going in the positive x direction, which if I jump back is what we're showing from our figure, right? We had -2, but it was -2 with respect to our datum.